Hey there, David Wong, and I just wanted to sort of finalize the last few videos that I made and kind of concretize this learning by looking at the paper that introduced these cycles of elliptic curves in order to do this IVC or PCD or whatever. And so the paper is called Scalable Zero Knowledge via Cycles of Elliptic Curves. I believe it originally came out in 2013 or 2014. I think it was published in 2014. And so this is often referred to as BCTV14. Um, so if you look at the paper, I'm not really gonna, go through the whole thing, but I always like it when someone talks to me about a paper and I kind of goes through the paper with me and shows me where the things that they just explained um, fit in the paper. So I'll do that. That's going to be a short video, but if you're interested in reading that paper, that's pretty old, but I believe it's the best paper to explain recursion. Um, then I'll help you get into that paper. So there's a part about pairing curves that's not very interesting, and there's a part um, about uh, about tiny thing that also I don't really want to talk about. What I want to talk about is how they build PCD via these cycles of curves, and it's very well written. I really like this paper, and it starts by giving some intuition and incrementally building from it. So basically, so here's the intuition. They say, here's our circuits, and we have this issue of like that explained in the cycles of curves thing. So we're gonna use two curves. I guess one curve will be over the field alpha, and one curve will be over the field beta. And so we'll first have a circuit that will create a proof, and then it will get verified um, within this circuit that will create a proof as well, which will be able to be verified by this circuit again, and so on. And so let's look at it. That circuit takes a public instance, so an instance, so that's the public input and a witness. And the first thing we do is that we parse the public input as two verifier keys, and Z, I believe, is the output that we're producing. That's the state that we're producing. You can think of it as uh, in our logic, we have some application data and we want to do something, we want to compute on some state and do something. So this is the resulting state that we create, the new state, the next state. Then we parse the witness, and the witness is some local data. So imagine if for a blockchain, this is the new block, this would be a bunch of transaction, and Zine would be the previous block. So that's the output of the previous computation. And this is the proof that come up from the previous. Basically, we have a previous proof that computed a new state. That's the previous state that it computed, and that's the proof. Okay. And then we say that if the proof is zero, is set to zero, then we know we're in the base case. That means there was no proof that came from before, because at some point we need to start. So we set that to one. And if it's not equal to zero, then we're not in the base case, so we set that to zero. There's many ways to figure out if we're in the base case or not, but that's just a trivial way to do it. And don't hesitate to pause the video if you need to understand these things, of course. Um, and then, of course, at this point, we verify the previous proof. To verify the previous proof, we take the verification key of the previous proof, um, and we pass the public inputs. And in the public input, you'll notice that we have the same verifier keys and the output of the previous proof, Zine, which is the input for uh, these circuits, the application data, the application logic, but it's the output of the application logic of the previous circuit, and then the proof that produced that. So we verified that, make sure that it verifies. And then the application data comes, the application logic comes in, and the application logic makes sure that Z is the output if you apply the local data to the inputs. And we also pass the base case Boolean because these things might be the same. Basically, there is no previous there's no previous output or input if we're in the base case. So we might here, if b base is 1, we're in the base case, we might say just set z to like some hard-coded value that we agree. The hard-coded value might be 0 or 1, or in the case of a blockchain, it might be a number of addresses, a Merkle tree representing a number of accounts and how much they have. So that's pretty much a circuit. The only thing that's sort of weird is that we're passing the verification keys as public inputs. One reason we pass at least that verification key as public input is that when we have these circuits, when we're writing it, we don't know the verification key of that circuit at the moment because we haven't compiled that circuit. And so the only way to get the verification key of ourselves is to get it from a public input. The next circuit basically does the same thing. There's nothing really different. It does the same thing. There's the same kind of logic in there. And then they explain that there's a few problems. What's the problem 1 and problem 2? Let me remember. Yeah, your application logic is kind of defined over a field, and if you have to implement it on 2 fields, it's kind of a mess. So what they end up doing is that they only have the application logic on the first circuit, and the second circuit is just to wrap the first proof and to create a proof that that can be verified by this circuit again. And so you only have logic in one circuit, which is simplifying everything. And by the way, sometimes we call that the step circuit, and this circuit we call it the wrap circuit because it's just wrapping your proof. Problem 2 is that the verification key is too big, and yeah, I can't remember exactly what their problem is, but the verification key has a length that's greater than the public input, and so that's what I explained previously. What you end up doing is that you pass a digest in the public inputs, and then you make sure that the hash of the stuff is equal to that digest, and the stuff is the a verifier key here. So that's the hash function trick that I've talked about in the last video. Notice also that since this thing is not doing any application logic, we're just passing the output of these circuits directly. We're not doing anything with it. We're just passing it to the next step. I think there's nothing more to understand here. They still go to the next thing because they have more problems. But I believe there isn't much that happens. They basically put everything in the hash, I think. And they also, I think, hard code. Yeah, the verifier key of one circuit is actually hard coded instead of being passed as the public input, which I believe should have been done in the first place. I don't know why they didn't do that. But here they decide to hard code. They decide to hard code the step circuit verifier key in the wrap circuit, which makes sense because you compile that first. You know what's the verifier key, so you can just hard code it here. But at this point, like I said, you don't know what's your own verifier key, and so you have to make sure that you have access to that. Actually, what am I saying? No, sorry. Let me rephrase. This guy knows what the verifier key of this guy is, so they can, yeah, that was correct. But this guy doesn't know what the wrap circuit verifier key is. And so here they have to get that as public inputs. And the public input comes from here, and so it's a hash, right? Remember, but it's a hash of this guy's verifier key, which they don't know because they haven't compiled themselves yet. So the hash is passed from the outside. But that's basically it. I know I went kind of fast, but you can pause the video. You can yourself go through these steps and understand what goes in. But it's really a lot of it is about deciding that the logic is going to only happen in one circuit and not the two circuits, using a hash function, which I've explained also, and passing the output of the logic um, to the next step function. And that's it. And hopefully that concludes the last, I think, 3 videos that were really mostly talking about tricks that are explained in this paper. And you can sort of see them explain the paper, and hopefully that was helpful.